introduction. Who am I? I am not a musician, or am I an AI researcher? I studied economics. Then I learned Python back, the first Python cohort here back in 2014, graduated in May. So I'm not an expert by any means. But that's not really, expertise is not the theme of this talk. The theme of this talk is much more, I have no idea what I'm doing. Let's see if we can maybe kind of sort of get something cool out of this and learn something along the way. The success of this talk hinges on the assumption that it's interesting and worthwhile to confront the opportunity, even if I've bitten off way more than I can actually chew. So let us begin. All right, so we have to get into this right now, because otherwise the rest of the talk isn't going to make as much sense. So continuity versus discrete things. Basically, if you've got some concrete set of things you're picking from, like you've got A, B, and C to pick from, that's discrete in some sense. It's also discrete technically if you've got like any integer number greater than 0, because you've either got 1 or 2. You don't play around with 2.5 or 2/3 or whatever. And this is important because computers, as we know them today, we all use digital computers, and digital computers are operating on discrete stuff. You've heard this a lot of different times. I think 100 times before you're 15 years old. Computers see everything as ones and zeros, which is really boring and not helpful to anyone. But you hear it a lot, and it is true, actually. So what does that actually mean? We'll get back to this. But here we go. So this is a Python built-in function. We're going to cover a little bit of Python, then we're going to leave again. And the only thing that's important about this is the letter L. And if you get an ordinal number, if you do this ORD function on L, L is actually a character. And the integer value for that ASCII character turns out is 108. And if we go in here and we actually like capitalize this, oh, how great is that? Capital L is 76. Why is that interesting at all? Because what your computer is actually working with, like I mentioned above here, if you're actually looking at like hardware stuff, it tends to be in hexadecimal, which is just a convenient way of looking at binary, because we can do immediately after this, which I researched. Oh my God, no, we can't actually. No. So we'll just do it in the same thing here. We can do, instead of hex, we can do bin, which gives you a binary representation of this integer. 76 is not binary by any means, but if we actually go and get 76 in binary, okay, there you go. This is the string of binary digits that is 76. And we could do this really boring thing where we go through and we add up powers of 2 to get to 76, but we're not going to. But it adds up to 76. It's instructive, and you're going to hear it a lot of other places if you look at all into binary anywhere. And so I won't bother trying to do it here, because I'll just fudge the math. But, all right, so everything we deal with in computers ends up boiling down to binary. Binary is very discrete. You've got 0 or 1. But we do a lot of things that aren't strings of letters. We do a lot of things with more than just integer numbers. So what's that all about? So we also have floats. Hey, oh, cool, these are the cells I was looking for earlier. Thank goodness. So a float, of course, is something along the lines of 0.11123, whatever. The great thing is, Python doesn't keel over and die when I do that, because it's okay with floats. There are all kinds of fun programming languages out there that will freak out and get angry with you if you conflate integers with floats, because under the hood, floats still look just like this binary bit. There's actually just a lot more binary to it. If I knew a handy way to get the binary representation of that float, that'd be handy. But typically, you see this is only a couple of binary digits. That's really compact. If you want to represent something like this, you need more binary digits than that. There's probably a way to do it, but we're not going to try. So we can actually represent numbers between integers, also known as real numbers. Kinda. Technically what we're doing here is just getting easily represented numbers like this. There are numbers that are irrational. They're real numbers. They exist between 0 and 1 and 1 and 2 and everything. They exist, but you can't actually come up with a succinct way to express them because it keeps on going infinitely. Okay, so why is this all important to any of this? Hopefully we have something. Okay, okay. So Zenos Paradox. Zeno of Illia, there are two Zenos, Zeno of Illia, proved, logically, that motion was impossible. And he did it, of course, by saying, if I were to walk over and slap John, suppose this is my goal. I start walking towards John, but before I can slap him properly, I have to make it at least halfway to John. And before I can make it halfway to John, I have to make it halfway between where I am now and the midpoint. And the actual, it's an infinite progression of halfway points between me and him. And I can't even get started with the first bit before I can, because in order to start with the first bit, I have to go halfway to it. And so motion is impossible, and I cannot, in fact, slap John. But if I actually want to, as a matter of fact, I can. It'd be really easy because my arm, as it swings through the air to slap John, manages to cross through an infinite set of halfway points. Every possible point, rational and irrational, all the real points between my hand and his face, it does in one fell swoop. But as we've covered, we have to really kind of fudge it with all this kind of stuff, because what we have, instead of the complete space between my hand and John's face, is a bunch of discrete stuff. So everything we do today, we do with digital computers. When you actually get down to what's actually doing the real work, there's a CPU in here, and it's doing something along the lines of, we don't want that, we want this. You take this binary number, you've got one set of binary digits, you got another set of binary digits in a register. You do really boring things like add them together or take their differences and that kind of thing. And everything you do, in fact, all the cool stuff we're looking at here, this is really groovy CSS and JavaScript has made most delightful presentation. This all, in fact, boils down to really basic stuff operating on binary. And that works for everything. We were pretty good there. But it does not have to be that way. There are such things as analog computers. An analog computer uses continuous stuff. An analog computer, I guess in the analogy we've worked out here, does actually swing its arm the full way through some set of space and potentially can hit all the infinite things between it. And you can use voltages and hydraulic pressure and physical distances for that kind of thing. And in fact, this is actually how computers used to work. If you've ever seen a slide rule, that's an analog computer that uses distance between stuff. Come on. Don't do this to me. Okay, cool. Yeah, if you want to find the middle of a board, or this desk, I guess, you want to find the middle of the desk, you could take a ruler, and you could measure the length of the whole thing, take that number divided by 2, then that halfway point that you've figured out after measuring it, you measure from one end to the middle, and that's about the midpoint. Or you could take a string. You stretch the string from one end to the other, you pinch off the length of the desk, take the two ends, stick them together. The half length of string reaches exactly the midpoint, where exactly is plus or minus. I'll let a little bit of it slip and it won't perfectly stretch out. But it's the same way of doing it. In the case of the ruler, if the ruler's got really wide markings between the measurements, say it's it measures out feet. If I measure this out and I say, oh yeah, okay, I guess it's about 5 feet. So the middle, I guess, is 2 feet, because we can't do 2.5 because it's not measured that fine. So we measure out 2 feet from the end, and it's here's the middle. And you could do something really fancy, I guess, where you measure out 2 from the middle there and you try and go back in the middle. But that error between the finest measurement you have and actual real middle of things does count. But this doesn't trip us up, because what we do instead of worrying about the difference between digital rounding off of stuff and what you'd get from an analog computer is we just throw a lot of extra markings on the ruler. like, tons and tons of progress over the last however many years is, let's shove even more computation and RAM and everything into this so we can measure things down to very, very fine levels. Because earlier I was joking, kind of, about, we're using how many different binary digits here. That's really wasteful. We need to conserve that. We can actually represent tons of stuff. This is really cheap, relatively speaking. We can do a lot of that. So there we go. This is an analog computer, the MONIAC. This is the Monetary National Income Analog Computer, and you can't tell from looking at it, but this runs a simulation of an economy. And it does it by running water from the top to the bottom, and there are little levels that are something like, the balance from trade and employment and that kind of stuff. And the flow of the water through it's continuous. This is something that somebody started playing with in their garage, and it turned out to be really accurate, like within 2 percentage points of whatever they were trying to simulate. You could do this whole thing in a digital computer, and we actually do today. You could do it on paper, and they did back at the time. This is like from around the 50s or something. But this was fun to do. And it's a computer. It simulates the macroeconomy. So why don't we use analog computers for everything? Yeah, it's really nice, but digital computers work just fine. And I think anything you can do with an analog computer, you can also do with a digital computer. And unlike the analog computer, where in order to get this to be really accurate, you have to spend all of your time like caulking things better so that it doesn't leak. You've got to get really fine-grained accuracy to actually make sure the water's flowing through. And if there's like a lot of evaporation going off, that really throws off your simulation. But with binary digits, if you want more accuracy, you just add another binary digit on the end, and it's twice as accurate potentially. That's kind of hand-waving, but we'll get into that a little bit more. So that's why we don't use analog computers for everything. We could, it'd be fun, but we don't have to. And with the exception of quantum stuff, anything an analog computer can do, a digital computer can do, except for quantum stuff, which is why quantum computers are interesting. That's hard to simulate. You can, instead of simulating it, you can actually do quantum stuff, but that's a subject for a different talk. Okay, so actually simulation is a lot of things, but it's also kind of how you can get at continuous stuff with digital stuff. Oh, there you go. Yeah, quantum stuff. I actually left that in here. All right. This is what we do. So specifically, this is a really cool simulation. We've got to click on it, because this is going to be way more entertaining than the first 15 minutes of this talk. So this is a simulation running entirely in the browser of light flowing from this middle here. Right now it's just a picture, but if I click and drag over to here, it simulates millions of rays of light going through all of these lenses, and so we can just pull this around. Obviously, one way we could actually simulate light going through lenses like this is you get the actual physical lenses. But the cool thing is we don't have to, because I don't have lenses, but I do have a browser, so we can even really crank up the resolution. And my computer's already starting to bake itself because there's a lot of simulation going on. But yeah, we can switch over to a laser. This is just me wasting time. But look at that. And yeah, right now it is cooking my computer because all of the simulation is going on in JavaScript on my computer through the browser. So that's wonderful. Let's see if I can close this and go back right to the talk. Excellent. So, this is great. Anything is technically an analog computer simulating itself. Geez, myself at this moment. So yeah, the great thing is, if we actually had a laser and those lenses, we could set them up on the desk and diffract light through them, and my computer wouldn't be growing really hot right now, because you can get more accurate by throwing more power at it, but like the simplest way to break it down is just to actually run the whole thing. All right, so sound is what we're actually interested in here, because this is actually about sound. I brought my synthesizer. It's really fun. And this synthesizer is an analog computer making sound. Computer might even be too much to say, but it is analog. There aren't actually any computer chips in it. There's just a bunch of circuitry, and electricity runs through all this, and eventually it goes out through my headphone jack and into my speaker, because I don't have real fancy professional type audio equipment, but this works. And so everything going through here is electricity. Electricity, it turns out, is a continuous thing. You can have, if you go from some voltage to some other voltage, it's going to go through all the voltages in between. And if you've got sound, the sound wave actually goes through different levels of amplitude, which we'll get into. We actually have a picture of some sound. There we go. So, this curve is an actual sound wave. It, as it goes along, it hits all of these points, but these blue dots are samples. If you want to actually get the continuous thing into digital land, you have to sample it, which means slicing it up at regular intervals. This is some really fast time scale. And at every point, you're measuring just one bit, which is actually a deceptive word to use here because it's multiple bits. We'll get into that. But you slice it up, and this is actually how you approximate it. When you actually go and you connect everything together here, and you sample it and you put it back together, this is a beautiful red sine wave. This blue thing is the actual digital approximation, and it is not beautiful. It's actually really janky. But you'll note these numbers on the side. It's not 11, 10, 1, and 0. It is binary. This is a case where you are taking something that's only accurate to 4 positions of amplitude. We should actually talk about sound. In this case, amplitude is the up and down on the graph. If something's not moving up and down a lot, it's not terribly loud. And as it's moving, it's not moving like this. This is a fiction. Sound doesn't move this way. C's move that way. Sound actually moves in compressional waves, which is really hard to look at, so instead we swap in nice, beautiful sine waves that you can actually see. And we're measuring it just at 4 points, and something like 1, 2, 3, 4, 5, 6, 7, 8 times. And each sample, this is a slice where you've blocked this off, has 2 bits of information, which is actually would be terrible to listen to. That wouldn't help anyone. But this is an awful simulation, an awful sampling of the continuous phenomena. But we can do better. You add 1 more binary digit, and this is still a horrible pyramid-looking jaggedy thing. But by adding the extra binary digit, we've got more accuracy in our representation here. So the actual set of binary digits we're using for all these different points are words. The word length is how many of these you have. And actually, if you care about sound, which people who work with sound do, you use long words. And then this ends up just being a list of these sound measurements over time, and the frequency at which you slice this up ends up being something like 40,000 hertz, which means that the thinner you slice this, the closer it approximates this nice curve, and the more realistic it sounds when you compare it with the actual continuous thing. So, now you know.
CD quality is 44.1 kilohertz.
There we go.
It's 44,100
right.
samples per second.
And the word length is, I think it's like 128 bits?
Oh, for CD would be 16 bit.
There we go. So yeah, you add 13 more of these. Kilohertz is, yeah.
That's how many measurements it's taking of that wave in that second.
Which ends up, if you care about measuring this accurately, or making it, which we'll get to, but if you care about measuring it accurately, more is better, but it makes for huge sound files. So,
and even here,
yeah.
So it becomes a law.
Right.
You just You're right. Well, you're not going to hear that stuff, so that's
Right. The beautiful thing then is, if it's really expensive to get up to, or if it was really expensive to get up to almost at parity with how humans listen to stuff, you just wait around and people make more computer storage and more computational power. And eventually the thing that was really hard and expensive and created gigantic several megabyte sound files, it becomes a lot cheaper relative to stuff. So that's why we are indebted to Gordon Moore. So, synthesis. This is what we were getting at. Okay, this thing makes sounds. And it does that by starting off with a bunch of oscillators, which are things that make actual continuous voltage variations. And then it runs it through a bunch of other filters and that kind of stuff, which is actually what some of this is doing. So if I yank these out, it sounds different. Sounds really different for some reason, which is, I'm not certain I actually like that, so we'll plug it back in. But what you got here, for instance, this is taking a low-frequency oscillator and plugging it into something entitled metal. So without this, the metalizer, we're playing this note, and if I wiggle this knob, will increase the sustain. So I could sit here and while I'm playing wiggle this, but there's actually a thing that actually wiggles at a constant rate. So if I plug its output into something that's essentially wiggling this for me, it wiggles it for me, and it sounds different. The same thing, you plug the envelope into the filter, which does something that's completely beyond me, because I'm not a musician, nor am I an electrical engineer, but it sounds fun. So, yeah, when we're actually doing this, it's all continuous. You're doing continuous stuff and other continuous stuff. But when you actually leave the world of the continuous that we're getting into here, you have to do the same sampling thing, and, you know, this sucker is definitely not. Oh, where is it, though? I genuinely don't know. I think it's actually continuous all the way to the speaker here, because we've got some kind of voltage variation in my headphone jack into the speaker. But it probably goes through something digital somewhere, or we know it definitely can because you can actually record things onto your computer. So, synthesis. Very fancy name for making sound. So this is a Moog modular synthesizer. It's like what I've got here, except way more expensive and way cooler. This is really big. And unlike, I've got like 6 things I can plug stuff into other things, this is all a matter of plugging one thing into another thing, and you chain it all together, and eventually you play a note on your keyboard, and sound comes out, and it gives you all kinds of control over different sound types. It's a lot of fun. You can play my synthesizer, John. It's actually fun. I guarantee it. So, but there are also digital synthesizers. You can actually skip this whole analog thing. This is like an actual heavy thing I have to carry around that costs money. But there are digital synthesizers that just doesn't bother with voltage variations. You can actually simulate the same thing or do even better than that by doing digital signal processing to get some kind of sound, and then you change the sound and you say, okay, we're going to squeeze the sound and make it, you know, a little quieter, but maybe shift it some weird way. So yeah, you can do the same thing. You don't actually have to get one of these. Why do I have a hardware analog synthesizer instead of just using digital synthesizers? Because I already have a computer. So the computer's practically already a digital synthesizer. You just have to use the right software. This is fun and has a lot of knobs that I can slide around, which is the whole point of having it. You can use it for other stuff, but really, if I tried to make any kind of fun sound on my computer, I'd be distracted by Facebook and that kind of thing. So I actually have this, but I'd be distracted by it, which is a rarity for some people, but I myself am sometimes sapped of motivation by distractions. So, how do we bridge the gap? The computer I've got here can actually steer the synthesizer, which we'll do now, or we'll attempt. It can't turn the knobs. You're getting into, yeah, they do. That's a really important significance. So we'll actually get this next fragment of a slide up here. So MIDI is actually how I can send sound to my synthesizer, and it plays the keys. Essentially, MIDI is a way of communicating things like which note you're pressing, optionally how hard you're pressing it, and that kind of thing. Oh goodness, what does it stand for? Luckily, we're in a browser. We can just hit Control-T. Not that big a distraction. Musical Instrument Digital Interface. There we go. Valuable information for this talk. So, let's see here. Do I have Reaper set up here? All right, Reaper is this thing. Very complicated looking. Ooh, I hope I'm actually connected. So if we're lucky, this won't take any extra work on my part. I'll hit play, and this thing, spread out across time, that's really hard to look at, is MIDI. And actually, for the sake of actually looking at it, maybe we can open it up. These are piano keys, which are not required for making music, but it's a great visual analog. And this is a C4 here, and I have got no idea why it's all split up like this, but this is kind of called piano roll. It's like a visual representation of playing these keys over time. Time's coming along this way. So as you go, you start off with one, and then you play this one here, and then this one, and so on and so forth. And it's not great to look at, but we're not going to look at it. We're going to hopefully listen to it. So if I hit play now, either I have things set up or I don't. It sounds terrible because at some point this used to sound good. It used to actually be on the synthesizer, but then I yanked it off and it got converted to MIDI. But this is playing the synthesizer as if I could actually press buttons really fast, but I can't. I'm not a musician. My younger siblings took piano lessons. I did not. I played the trombone, which I didn't stick with because, I mean, how many times do you play trombone by yourself? If only I had the technical ability to actually press keys in an organized way and in time, but I don't have to because I have this. And that's entirely enough of that. But, so, oh wait, well I guess we'll have to specify. So MIDI encodes information about how fast you're pressing keys, what order you're pressing them. If you're pressing them at the same time, which I can't. As a matter of fact, this is a monophonic synth, which is a long word for saying it can only really play one note at a time. So if I try and press two keys, it just sticks with the first one. No, it sticks with the lower one. I changed that. It used to stick with the most recently pressed one, but then I messed with some settings I shouldn't have. So, if you want to do really cool stuff with chords, you can't. You're out of luck. You should buy a vastly more expensive synthesizer, which I will someday. But while this is playing this, which we'll set to rolling here, we'll turn it down a bit. So the actual, I'm thinking about it. That is sad. So while the computer is actually running the keys, I can actually change the things that affect the sound. Because MIDI doesn't actually have information about things like effects and that sort of stuff. There's some stuff, but the actual bit of music, all together in one package, includes both the MIDI information and then whatever kind of patch set I'm running this through. This is significant later because that means we can't just have some kind of text file that has everything we care about in it. Well, we can. It's not MIDI. MIDI does not have all of the things we care about to make really cool sound. Because really, the MIDI itself, we're going to make this sound really boring for a bit. My apologies, everyone. MIDI by itself is really dull. Let's see here. Yeah, there we go. And see here, it's trying to like show me up by sounding kind of cool. But the point here is that if you don't actually do any of the extra stuff on top of it, you might have really complicated, interesting music, mind you, just with the one voice. But it doesn't have the same pizzazz as, say, music I actually care about, which, at the risk of embarrassing myself, I actually have loaded up. Oh goodness, we're going to digress into SoundCloud a bit, because this is important for motivation. Why did I get interested in making music like this? Oh, of course it's going to do that. All right. I got really into trap music, which maybe you know about, maybe you don't. Well, get ready. Hold on to your pants. Now that's the same thing over and over again, kind of, with some minor variation. But why it's fun to listen to is that it has character. And that's the echoey stuff and the fact that it sounds like... I can't control the volume, so I guess we're just stuck at a fixed volume. That's really cool. But I'm not to the point where I can actually make that just with this. And it might take some extra work. But the actual character we care about ends up being stuff you make with this business here, not just the key or the sequencing. And so we need to find some way to actually get into making stuff that sounds like that. And so now, a long time after, we actually get back into kind of the theme of this whole talk. Can we do this with machine learning because I'm lazy and don't know how to do things? Machine learning in a nutshell is, instead of telling a computer explicitly how to do something, why don't we tell it how to learn how to do it on its own if we give it a lot of hand-holding, and eventually it might get really good at it, and then we sit back and let it do all the hard work. What kind of stuff do we do? You can do things like classifying pictures, making choices like, okay, which move do we play in a game of chess or Go or that kind of thing? Or should we buy this stock? That kind of stuff. It's hard to do because computers don't actually care about the things you're trying to teach them. You have to plod along the whole time and get really specific about everything you're doing. But typically, you have something like supervised learning. Supervised learning is machine learning where you say, here's a bunch of examples of stuff we care about. You've got a bunch of pictures of dogs and a bunch of pictures of cats, and you essentially show it, these are dogs, these are cats. This thing, I haven't told you what it is. What is it? If you get it wrong, okay, we're going to go back to the picture of the dogs and cats again. You could also do unsupervised learning, which is interesting but a bit beyond this talk. So, kind of. We'll get back to that. So, we can teach something to classify stuff. You can ask your machine learning algorithm to say, all right, this is a cat, or a dog if it's in fact a dog. But that's not the same thing as getting a computer to make something cool and creative like music. How do we do that? Well, Google beat me to it. They did this deep dreaming stuff. In this case, they've got little pagodas magicked into this rocky landscape. How did they get magicked there? They had something that could already look at images and would do things like say, this is a bunch of boring rocks in the middle of nowhere. This is a pagoda. This is some kind of intricate cathedral-looking thing. And instead of asking it if this was a set of rocks, which it obviously is, they said, okay, we're going to give you this picture. Now change things a little bit at a time until you're pretty sure it's maybe a pagoda. And so you go through and you flip one pixel at a time, or you do something way more sophisticated than that. I don't actually work at Google. But yeah, you change it so that instead of going from thing you want to have labeled to the label, You take something that you don't care what it is, and you give it a label, and you say, okay, now go in reverse and make it look more like this other thing, which is how you get horrifying stuff like dog noses and eyes all over stuff you might have seen. And that is kind of how you do it. So, get ready. Talks about fall apart. Neural nets. What are neural nets? Neural nets are, in fact, what they were using here. This is, in fact, the product of a convolutional neural net. The convolutional bit we could get into, but I don't want to because, man, we've only got so much time. And it's a kind of neural net. Okay, so what's a neural net? A neural net, some people describe as being like a brain. Oh, there we go. Yeah, what are they? This is a neural net. And this is hideous to look at and has already put most of you off. But it's actually really simple. You've got something, and this ends up being something like individual pixels from an image, and they've got some value. And each of these little neurons, each of these circles is a neuron in this case, depending on its own particular special weight, decides whether or not to signal the next one down the line. And so each of these little arrows connects to another neuron in the next layer. You've got these layers. They either shoot neuronal activation at a neuron or not. And then in turn, each one in the next layer decides whether or not it's going to fire. And it decides that based off of adding up all of the values of the things that fire into it. And then it fires the next layer, and eventually you get something that kicks out. And this isn't helpful because this isn't going to actually classify things. Well, this could classify something. This would be if you have 6 different things feeding into it, you can have one of 2 different states kicking out, because this last one either decides to fire or doesn't. So, why are these cool? They're kind of cool because we think this is kind of how the brain works. Really, it's not at all, because it happens all in one moment of time. They're not talking to each other. The ones on the top only send things down to the ones on the bottom as it flows through. But it's kind of a simulation of how neurons kind of work, which is fun because simulation, other stuff. So you could actually have each one of these things run a tiny little program where it only cares about stuff coming into it from outside. You could actually rig it up entirely with circuitry. And you could set this out just by getting a whole lot of these. And this is boring. This actually can't do much interesting stuff. But because each of the little neurons is actually really simple, and because we've got computers with lots of RAM, lots of memory, and lots of computing power, we do this, but instead of having 4 here, you do something like thousands and thousands and millions. And you get into really big numbers because it's really simple in one sense, but you keep scaling it up because, we can. And then you get fun things like identifying pictures of dogs looking at bowls of cherries and that kind of stuff. So what are recurrent neural nets? They're kind of like that, but they've got the ability to look back in time. There's a time element, kind of. This thing happens all in one go. You feed it something that's got like 6 pixels, which would be impossible to look at, and then it decides. And recurrent neural nets aren't quite like that, but we just need to keep on going with the talk. So here's our problem. Well, we'll take a brief interlude here first. Look at an actual working, or in our case, not actually working all that great, neural net. Here we go. We've got actual code. This is using NumPy, but also using Keras, which is a Python package that is kind of a layer on top of Theano, which is another Python package, which uses another Python package, which allows everything to do cool stuff. This is just really good at doing the math that we care about because, as we said earlier, each of these is a very simple bit of math just with the one neuron, but you're doing it a bunch of times, so it actually matters. Otherwise, it'll take forever, which is significant, you'll see. And this is just a bunch of handy stuff. You see, we're importing things from layers. So the layers here, in this case, instead of actually having to program something by hand, You just import them. We've imported them from a thing that already exists, which is just so terribly handy because it's really character building to have to do this all yourself, but I'd rather not. And so each of these layers we just import, and there are all kinds of different ones. There are more kinds of layers than I have any idea. And you just stack them together. Where does the stacking happen? We create a model, and then, yeah, we just do this thing over and over again where we say, you know, I'd like a cookout combo with a hamburger and corn dog, one of those beef quesadillas. But you just keep listing it here. And each time you call add, it just stacks the layer cake of artificial neurons. We never had to actually handle an actual artificial neuron because they're like gray and slimy and gross. But it does all of this here. It uses some convolutional stuff. And so, what are we going to try and predict with our neural net? This thing in xtest, xtest index 0, this is the first item in a list of things called xtest, which is just terrible notation. I never would have done that, but someone called it xtest in the example that I'm running here. And it is just horrible to look at. It's a bunch of zeros with the occasional number thrown in. There we go, there's some numbers. This is abominable. No one cares about this. You are losing interest. So what is this actually? This is, and it'll be really helpful that we've zoomed in. Oh goodness, it broke. No. It's in a different window maybe. All right, so the thing is, we don't know actually how far we are along the process of doing this. What we're going to do is grab just this line where we load this MNIST data thing. Non-descriptive in the extreme, in fact, an abomination. We go back down here to the end, cross our fingers, and hope this works. And actually, it could be kind of quick. What we care about is looking at it. And we care about this line. Actually, we care about... Oh, God, no. You didn't do that, Gordon. Okay. We care about these. All right. So we've got an xtest thing that we've just loaded anew with these arrays right down here. When we use pill, or in fact pillow because pill is an impossibility to use, let's hope this works. This will be really embarrassing otherwise. There we go. It's a tiny number 7 written in a tiny, I think this is 26 by 26 pixel square. We could try and zoom in on it, but I'd rather not. So this is from a data set of written digits, copied from like postal forms that have been filled out. And this is a classic machine learning trick where you try and teach a neural net to identify these written digits by giving it a bunch of these little pictures, and then the letters that they actually correlate with. Let's see if we can do this again and get everything transformed the way we want it. Cross your fingers, folks. Because that'll run. Because we had the neural net isn't working with it shaped like the image. It yanks it out and convolutes it back to a bunch of arrays, which we can look at, but I digress. So right now, if we load up our machine learning, our neural net has been stashed. Because previously, we actually trained this, where you go through and you tell all the little neurons, okay, this is a 7, you should come up with the answer 7, correct yourself so that it actually matches closer with what we're looking at. I ran it here, and it takes forever. Are there times with this? This was a long, long time. So rather than sit here and do this live, we're going to cheat and load it from something I'd saved to some JSON and some H5 stuff. We run this again, it'll complain because there's some kind of deprecated thing stuck in Theano somewhere that it doesn't like, but it doesn't matter. There we go. That's run. We go back down here. This won't work again because now xtest has been convoluted about. But if we make a specific test say we're just interested in the first thing, which we know is the 7. There we go. If we predict, well, we'll just predict on the whole thing, and then we'll get good stuff back out. No matter. It's going to predict. Right now, all the neurons are firing, which would happen theoretically instantaneously, but you actually have to run this on the computer, and it's involved. Then, okay, cool. Here we go. We get predictions out. Notably, this doesn't say 7 anywhere. This is actually a list of 10 things. The first one's 0. If you know your scientific notation, this is a very small number. It's e to the negative 13. Small number, small number, small number, small number. And then we get this 1, which is not actually 1 because the probability should all add up to 1, but it's about 1. It is very certain that this thing here, which corresponds to 7, is actually the thing it's predicting. It's worked. We have triumphed. Look at this. Get ready. Now, if I've transformed the array that previously had this list of stuff, now it says 7, and these are the predictions for everything because we've gone backwards. So, what have we learned? Neural nets are really cool until you try to actually do that.
Is that array 0 through 9? Is that array for the prediction?
Yeah.
0 through 9. Okay.
0 through 9. Yeah.
7. Cool.
Yes.
That's really cool.
So, yeah, there it is, working live. Let's make music with that. Notation by itself, like I demonstrated earlier when I tried to make the synthesizer sound boring, is kind of boring. It's not going to give us the music I want to make. But sound is hard because earlier we were using a 26 by 26 pixel black and white image, and it nearly killed my computer and I had to stall for several minutes. And machine learning, where you say something like, here is 500 terabytes of music. And this terabyte of music is the music I want to make, so just learn all of it, and then we're going to ask you to produce music that I like, is not feasible. I apologize. But first, let's just think about this. Okay, all of our options right now, we could do something like feed it notation and try and get notation back out. Where you say something like, here's a bunch of stuff written, doesn't actually matter because the neural net doesn't really care what kind of stuff we feed it, but we could feed it like MIDI or something close to MIDI, because MIDI you can't look at. Turns out if you try and actually open one in Vim, it's like a bunch of byte characters, not fun. Or, I mean, it's okay, you can escape, but you do something like, say, ABC notation, which actually represents, we've actually got a great example of it here. Here we go. We'll zoom back in. This is a completely text-based representation of music. In fact, a representation of the ranting Highlandman, or alternatively, the white cockade. But this is music. And we could presumably do something just like, you want to zoom back out? Please, please, please. All right. We could do something like, we'll give you a bunch of these, which we have a bunch of this, actually. We'll get back to that in a bit. Comes up later. And I want you to make more music, and it turns out if you have ABC notation like that, you don't need machine learning to convert from ABC notation to MIDI. That's a very, very solid rule-based process by which you say, oh, you'd like to play a C. You play a C, and that doesn't need machine learning. Someone did a lot of work actually writing that, but you can convert that to MIDI and back. We could do something along the lines of, all right, we're going to give you a bunch of notation, but we want you to output sound. We already have one of those. We actually just ran it here when I, hooked this up to, oh god, it's quiet and boring now. When I hooked this up earlier, you could maybe get some kind of machine learning thing where we actually have filters and effects and that kind of thing, but that we've got. We could try and go from sound to sound, and I did some research. I thought it was going to be really great, but it turns out some folks have tried to do their PhDs on this thing, and they came out with really terrible results where it was really noisy sounding, and they trained it on Madion, and they'd overfitted. I think they're like a French electro punk band. Does anyone know? Correct me if I'm wrong, please. I'm the expert here. They trained it on this music, and it was mostly, oh, we're getting to Daft Punk. Get ready. It was mostly like noise, and then you heard some of the exact same song that they trained it on, or one of the songs they trained it on. It was a complete failure. It was actually really cool, but it took them a lot of computational time, and it was, in my opinion, not all that great. And we could do something like, all right, I'm going to give you a bunch of music, and I want you to like extract MIDI from that. And it turns out this is like, there's money in this. People will pay for this kind of thing. And people have been working on this for a long time before now, without machine learning or neural nets like we're playing around with here. And that's kind of cool and has some potential because, you know, that'd be really handy, where I hold up a microphone to something, or I get a sound file. I'm like, okay, now play the stuff I care about on my synthesizer so I can sit and listen to this thing and twist the knobs and have a good old time. But you need a lot of data where someone's actually played something in a sound file, and they happen to also have a MIDI representation of it. And those things aren't like one-to-one. You could have a number of different ways of coordinating between the two. You can have something you don't really know the one right way to get the notation. Unless you like steal somebody's stuff, you grab Dead Mouse's laptop, you run away really fast, and you've got all of his saved projects from his digital audio workstation, and then you've actually got that stuff and you're fine. But that seems...
Is that how automated takedowns? Like automated takedowns of music, is that how it would work?
Ooh, actually, you're right. This is the same world of identifying things, fingerprinting sound and that kind of stuff. Even if you like throw in an extra 10 seconds of unrelated stuff, and then you put an actual song and you upload it to YouTube, they'll find you because of this kind of world of research. Which, again, I'm not an AI researcher. I don't actually know anything about this. So this is the world of options as I've considered it. It's actually kind of tough. Let's take a look at this thing that I've had running in this other window here for a while, where, so earlier I said you need a lot of data to actually do this stuff, and where we're going to get a lot of data for like free notation of stuff. It turns out people don't just post MIDI for all of their songs everywhere for you to get, but we have a gigantic collection of Irish folk tunes, all for free. This is all in the public domain. We've got a lot. There's actually, this is just one file. There are 4 more files just like it, jam-packed, thousands of Irish folk tunes. And so I've downloaded this text file. And while we've been having this conversation, I've been trying to recreate what this individual's done. This is the successful output here, inspired by recurrent neural networks. This person has run a recurrent neural network on all of this Irish folk music, which we do because that's what we have, and generated this nonsense title. Listless, these are not words, but it managed to learn enough to give it kind of names. And there we go. This is an artificial Irish folk tune. It's a little cluttered. Yeah, this is a great success. On the other hand, a not so great success was what I've been trying to do over here, where earlier I set up a character-based recurrent neural net using Keras, which they've got examples of this. I just said, oh yeah, that's the example. And I tried to get my super secret source of ABC notation of music that may or may not be Irish folk music, just for myself, just because I was curious. And I started this a while back, and here we go. We've created the model, and now it is compiling and training the model. Oh, there we go. Hey, there. Look. This is the music it's trying to generate as we go. It knows there are letters in ABC notation, and it kind of likes these slashes. Sometimes it likes not music-looking stuff. But here we go. This will be done. Oh, we've gotten through. We might even have stuff. I don't know. This takes a long time to go, and this is why my computer's burning itself up. So, we're going to say this has been a catastrophic failure. In the search for how do we do all this stuff with computers to make cool sounds? This might be easier to do if I spent a lot of money on fancy hardware. I hear you can buy expensive GPUs and make machine learning go really fast that way. So I'm still interested in it, but you know, I came up with this talk on a whim, like off the top of my head a month ago, when they asked me if I'd be willing to lead a talk. I was like, oh yeah, I just got a synthesizer. I can totally learn how to use neural nets to make music. So this gentleman spent a lot of time getting this stuff to work, and he still can't even get his neural net to come up with sensible English language titles. We've tried it with notation. It's still running. I'm going to need a new computer. I have bad news, of course. I only have Irish folk music. If you actually want to get enough data to actually make cool stuff out of this, you're going to need some better source. If you're trying to do sound stuff, I hear there are ways, if you don't care about laws, to get lots of music from off of the internet. So that would potentially be something you could do if you have a lot of storage space, because it could get really big, and a lot of time, because it's got to comb through all of it. But you know, my notation thing right now, I've just got Irish folk music, and that's not going to get us to very loud, brassy trap music. So this has been extremely disappointing, Gordon. I feel let down. As do I. I learned a lot. But don't worry. Turns out that there's actually a very satisfying resolution to this. We can actually make much better music by programming than I can with neural nets. So, what do we have? Sonic Pi. What is Sonic Pi? Sonic Pi is somebody else's doctoral thesis, but instead of making really bad Irish folk music, this person did a PhD on like human-computer interaction and wanted to make a specific programming language just for teaching people to program and to make music with synthesizers and stuff. This is all software synthesis, and this is, in fact, just kind of Ruby with slight variations. So this is cool. I stole this. This is something I wrote. This is an original creation that I did the first 3 minutes when I found Sonic Pi, and it actually is kind of neat. Can you not hear that? It's playing off of mine. Okay, we'll stop that. We'll have to figure that out, though. Sound. Let's see here, because you're going to want to listen to this next one. So this is something I created. This is actually using Super Collider, which is a fancy, very intimidating software synthesis thing. This is the Daft Punk song Aerodynamic. It imports 2 samples, which I realize now in this very long talk I've completely glossed over the difference between a sample and like a synthesizer wave. Sample is just a sound file. We're going to play it over my computer speakers. You can all crowd around closer to my laptop. But it's playing all of this live. You actually thread different loops. And it's really cool. And I might actually learn how to do things interestingly without trying to cheat by teaching the computer to do this stuff for me instead. But there you go. I recommend this. This is really handy. It's very well designed. So, what are our takeaways here? Machine learning is really hard. Not hard always because the actual concepts are hard to grasp. Virtually every concept itself is pretty simple and straightforward. Neural nets aren't hard. It's just a bunch of easy things where you crank the scale up and you shove a bunch of them into one neural net. But it takes forever and requires more hardware than I'm willing to buy for this talk. But making music's fun and can be cheap or free. Sonic Pi costs nothing to play with. I recommend you do so. This didn't cost nothing, but I think it was a valuable investment because I like twisting knobs. And so, oh goodness, it was. We'll have to look. We'll bravely go there here in a bit. before then, I'll just recommend this documentary, I Dream of Wires. It's on Netflix. The entire history of the synthesizer from that very large Moog modular we were looking at to the present day with this sucker. And Neural Networks and Deep Learning is a free online textbook that I grabbed one of their pictures from. It's kind of okay. It's technically fair use because I cite them down here. And Sonic Pi, cannot recommend enough. It's really cool. And I guess it got caught off here. There we go. The Introduction to Music Production class on Coursera with Luden Starnes is great. Tells you all kinds of things about kind of what I did a terrible job of explaining. And this guide to aerodynamic, you go through, you work it out yourself. Go look at all those things if this is even vaguely interesting to you, because you could do a better job than me because you know everything I know now. So, yeah, attributions. Not terribly interesting. Let's go back to this thing and see what we got out. All right, iteration 10. 206 seconds remaining. Did it go in reverse? What does it look like at the top? Let's investigate this. This concludes my talk. You're welcome to ask questions and goof off and everything else here. I had a great time getting into this. Wow, look at that! This is not music. Thank you. This is way too ambitious of a talk. Yeah, yeah. Oh, good. That would have been the smart thing to do, but I did not. I did the lazy thing, which is the theme of this talk, is get into it quick and dirty and see what you can get out. And this is what you can get out in this case. But yeah, if you're interested at all, let's take a look at some code here. Up here at the top, stepping into this. This is a text file. That same text file we looked at. It's all in one continuous string, I think, with new lines in it, which may be why it's so fond of those slashes. And then you get the length of it, and then you get a Python set of all the characters used in that text file, which is actually a small number of things relative to the length of it. It cares about each individual thing on a character-by-character basis. And it's trying to figure out, okay, given the previous character, what's going to be the next character? That's actually the prediction task you're trying to train it to do. Instead of asking it, okay, is this picture a picture of a dog or a picture of a cat? You say, here are the first 49 characters of a 50-character long string. What is the last one? We'll give you tons of strings, and you can guess. And then you can melt Gordon's computer. But then what you do in reverse is, instead of trying to get it predict the last character or the next character and one that you actually know the answer to, you just say, okay, predict the first character. It just guesses. Okay, now what's the next one based off of the last one you just guessed? And it goes through the whole way, character by character, and produces stuff like this. But it's entirely a matter of jumping from capital E to capital B to lowercase I. Of course, it's case. It respects case. Case is case sensitive, because to it, it's just the same.
It looks like there's like titles in there.
Yeah.
File maybe just dump one of those like, titles and different things.
Yeah. Yeah. Exactly. Let's get back over here to the actual file. We're just shoving the whole thing in there because I'm lazy. And it's got this structure of a title begins with a capital T and a colon, and then you've got a bunch of new lines. Of course, you can't see them here. They're just nicely tucked away. But it's completely agnostic to what you're actually doing. And here's the article that actually inspired this, the unreasonable effectiveness of mathematics and the natural sciences is not what we're going for. That's the original one. This one rips off Google. This one rips off the title of this paper. Come on, backspace. Recurrent. We've really bogged down my computer, what with We are stretching the world's capacity for machine learning here. Head and neck malignant. Oh, goodness. Able effectiveness. Oh. I wanted unreasonable, right? Not the able effectiveness. Unreasonable effectiveness. Okay, we're getting there. This is a long wait because I should probably kill that thing that's running up here. This inspired me. This is an excellent article. You should read it. It has great visualizations. It actually bothers to explain, oh, recurrent neural networks allow you to do things like, instead of having just the one set of pixels that you get the one digit guess out of, you can say, we're going to have maybe a string with 3 characters in it, maybe a string with 150 characters in it. The actual length of the input's not known. The one we did with the digits is hardwired, but this, pardon? Yeah, a repo that doesn't use Python. So I did the really rotten thing and tried to figure out how to use it with Python. Okay, it's got great visualizations. Here's a thing that's identifying digits, and instead of having it drilled down to 26 by 26 pixels, you give it something that might have 26 by 26 pixels, may have more than that, and instead of going over the full set of pixels, it actually goes on like a stroll through all the pixels and works out what it thinks numbers are. So what's a recurrent neural network? This is all dull because what we want to get into is the output, which will actually inspire you. We'll zoom in on this. You feed it the complete works of Shakespeare, let it sit and think for a long time, and going based off of just which character follows which other character, it's got some memory thrown in there, it figures out how to do this. This is actual language. This is no more complicated than the thing spewing garbage in my other window. It's just had more time and a larger source of stuff to work off of. But this is an actual Shakespeare. This is nonsense. But it's managed to figure out the whole people who are speaking have all caps. This is nonsense, but it's good nonsense. This is really exciting.
This is generated?
Yes, this has been generated by a neural net. I wanted to present something awesome like this, or that Irish folk music we listen to. But we learned more valuable lessons, I'd say. You can train it on Wikipedia. And again, that was all English, but here it is, like, embedding nonsense URLs in things. It's referring to other Wikipedia pages, some of which don't exist. But you can feed in things like, okay, yes, the Yahoo URL does not really exist, but it creates things like this. You can get it to create HTML. There you go. Oh, it's valid XML. If you actually plug this in, it's not going to have an XML error, not because it knows what an XML error and really cares about it, but because it's learned the structure of it well enough that it remembers to throw in a closing tag for everything. This is nonsense.
What's cool about the output that you had was it had the same structure.
Yeah.
It was like short, and then like go long.
And the recurrent character-based neural network is good at that. Maybe not so much at figuring out what makes fun music, but if you can figure out the right data to train something on, and a good representation where you got a lot of examples, that could be really fun. Someday. Turns out it takes more than a month to figure that out. You've heard of LaTeX? LaTeX it's like a markup language to make really cool functions. These functions have been randomly generated. All of these things, this means nothing. But look at that, you got things graphing at one another. There you go, proofs. It's trying to write proofs. Linux source code. You train it on the entirety of Linux source code, and it figures out things like things are ints. Again, I don't recommend running this, but this is exactly what the creator of Lissel's Stis here has done with a lot of this. And they didn't actually throw in any extra fancy formatting because this is the output he got. It actually gave it the title that we've been making fun of here. All they had to do then was convert from an ABC notation to something with a fancy score. I once studied music. I've actually forgotten what this is. Something clef. That one. How many clefs are there? But I've only ever encountered the two. Well, yeah. So, this is why I got excited about all this. There we go. It gave it an Intel mobile communications copyright. This is not intentional. This is learned by the neural network. But it's also got the GPL. But you repeat something to it enough, and it learns to output that kind of thing. Yeah. Baby names. Long baby name. Oh, those are individual baby names. Okay, I was going to say. Some of my favorites include baby. Which makes sense, because I guess if you're training on birth records data, sometimes you have to come up with a name for the baby. Okay. So here we go. Here we have actual samples from the training data where you've just started training the recurrent neural network. It's gibberish. But the difference between this and this, other than the use of punctuation and closing the actual quotations, it's figured out how to insert a new line in a way that kind of makes sense. And as it goes, yeah, they do look like words. It figures out the whole, you have a period and then you have an uppercase letter after that. Getting closer, kite vooch. And there we go. You get to this point where it's not a sensical sentence, but I'm not seeing immediate mistakes. Oh, okay, so here we go. This is not actually a helpful visualization because I'm even having a hard time explaining it. So they did some fancy stuff here where you're basing firing of neurons off of a particular character at a given time. I think it maybe looks a little bit better here. Neuron highlighted, so on and so forth. But this is kind of what it's working through. In this case, this was a reference to something in Wikipedia. And it decided to use this angle bracket here. But it also considered using an uppercase C, uppercase S, lowercase c, a lowercase p, and an uppercase a, where it always went with the most likely option, but it could have gone wieldy, or so on. Cause papers, so on and so forth. So yeah, how cool is that? Oh wow, so much to look at. You should read this yourself because it's an actual article and not something that I just scroll through and point to in the middle of a talk. But yeah, this is very cool stuff. There we go. Let's take a look. Is it still going even? Oh, it's going. Is it? But it just moved, right? Let's scroll up here to the side. It says it's still going, but now we can look at the full length of it. Too many things. We're not going to try and play this music. There, it's going. All right, cool.
It understands the title notation.
Yeah.
You don't think about it. You're like, yeah.
I didn't sit down with it earlier and tell it about how to write ABC notation. It just doesn't care. We just gave it a bunch of strings, yeah. Or a single string with some new lines in it. be precise. Yeah, there we go. That's the full talk. What we really ought to do is play around with the synthesizer and stuff. And I guess I'll figure out if there's cool stuff you can do with recurrent neural networks in the future. But that's it. Oh, look at that.
It's getting better if you watch that section as it goes along. It gets better.
Oh yeah, you'll scroll back down. Sorry. There we go. So
And that's only, what, like 11 iterations? Like, it's getting pretty good. Just a short amount of iterations.
right. So this is why like data engineering and big data and that kind of stuff is cool. Not because data has to be really big, but because if you want to do this kind of thing, you need people to sit down and actually parallelize things. Well, these definitely are words. This is talking about
The music section.
these. Yeah. Yeah, there we go.
It's getting better.
What you'd want to do, or what you actually do if you work at Google, is you figure out a way to split this up across lots of computers and access a bunch of different data. And then you do a really great job and you do things like win competitions, recognizing images and that kind of thing. But this is also fun. You don't. But if you do work at Google, you do this. So they do. So
Massive servers that will run this.
yeah. Oh yeah. Not just massive servers, but like things to put things onto the massive servers for you. Maybe I'm just focused on that. Are we done?
Yeah.
Scroll back up here. Oh no, it's still going. There we go. What fun. Yeah. You can leave whenever. I'm gonna eat some pizza. We can continue to have